Hello everyone, I am Dr. Abdul Malik from the Department of Electrical Engineering, Bahadur University, Multan. Welcome back to the design procedure of combinational circuits of digital logic and design. In this part, we will be discussing some case studies of combinational circuits that include binary adder, subtractors, and decimal adder. A parallel binary adder is a building block of the arithmetic logic unit of any microprocessor. A binary adder can be constructed with full adders connected in cascade, with the output carry from each full adder connected to the input carry of the next full adder in the chain, called ripple carry adder. In this block diagram, we have taken 4 full adders, and let's suppose if we have two 4-bit binary numbers A and B, with A as A0, A1, A2 and A3, and B as B0, B1 up to B3. And if you want to add these two numbers, we will be adding A0 and B0, and the sum will be S0, and there will be a carry. We will name it as C1, and then C1 plus A1 and B1 will be having sum S1, and so on. So the circuit that we have designed, we have applied the 4 bits of A over here and the 4 bits of the second number B as B0, B1 and B2 and B3 to the full adder, and we have taken the carries. We have yet an initial carry from the previous side, and the carry of this full adder is becoming the input to the next full adder, and so on and so forth. And thus each of these full adders, this first full adder will be adding 3 bits: the least significant bit of A0, the least significant bit of B0, and a previous carry C0. These 3 will become the input of this full adder, and there will be a sum S0, and there will be a carry C1. Now this carry C1 and the next significant bit of A as A1, the next significant bit of B as B1 will be going as input to the next full adder, and we will have yet another sum S1, and we will have yet another carry C2, and so on. So this whole circuit, when it is taken as a block, is taking inputs, one number A as A0, A1, A2 and A3, the next number B as B0, B1, B2 and B3, and a possible carry from the previous side, and it is providing us the sum of these two numbers. The least significant sum bit is S0 and the most significant sum bit is S3, and a possible carry. So this is called the parallel binary adder. Let us elaborate it in another case study example. Suppose we have a number A as 1011 and another number B as 00 and 11. When we add these two numbers with the help of a parallel binary adder circuit, first of all, let's take a least significant carry as 0. The sum of these 3 bits will be 0, and there will be a carry propagation. You have applied these 3 bits, the least significant bit of A, the least significant of B, and the first carry is 0 to the first full adder, and it is giving us the sum 0 and a carry 1. Similarly, these 3 bits will be added, and there will be a sum 1, and there will be yet another carry. This will be going to this full adder, and then these 3 bits will be going to this full adder, providing us the sum over here and the carry over here. And then lastly, these 3 bits will be going to this full adder, providing us the sum bit and the carry bit. So what we have done, we have applied the number A, we have applied the number B as input to this circuit and an initial carry equal to 0, and we have obtained 4 outputs starting from S0 to S3 as the sum bits and a possible carry C4. The total propagation time in the parallel binary adder is equal to the sum of the propagation delay of logic gates along the path from input to output. The longest propagation delay in an order is the time it takes the carry to propagate through the full adders, called critical path. Each bit of the sum output Si in the adder will be in its steady state or the final value only after the input carry to that stage has been propagated. Consider output S3 in the 4-bit adder. Inputs B3 and A3 are available as soon as the input signals are applied to the adder. However, the input carry C3 does not settle to its final value until C2 is available from the previous stage. Similarly, C2 has to wait for C1 and so on down to C0. Thus, only after the carry propagates and ripples through all stages will the last output S3 and the carry C4 settle to their final correct value. This will be a serious problem if the adders has a long bit length. For example, in the circuit that we designed previously was a 4-bit parallel binary adder, but if we have to design a 16-bit or a 32-bit parallel binary adder, which is a very normal phenomenon, then there will be a lot of propagation delay. In order to overcome the propagation delay issue, carry propagation in binary adder circuits are designed to resolve the particular aspect. We relabel the half adder implementation that we have had in our previous lecture as we name a variable pi as equal to ai exclusive or bi, and we label gi as equal to ai and bi. Over here we can see pi is equal to ai exclusive or bi and gi as equal to ai and gi. Now we can very easily see that since ai and bi are made available as soon as the input numbers are applied, so each ai and bi, a0, b0, a1, b1, a2, b2, a3, b3 are available as soon as these numbers are applied to the parallel binary adder, and in one stage implementation we will have PIs and GIs instantly. PI and GI settle to the steady state values after AI and BI propagate through their respective gates. The input carry CI to the output carry CI plus 1 propagates through an AND gate and an OR gate. If there are 4 full adders in that, the output carry C4 would have 4 multiplied by 2 is equal to 8 gate level from C0 to C4. For an n-bit adder, there are 2 raised to the power n gate levels for the carry to propagate from input to output. So, in order to overcome the issue, we will design a circuit called carry look ahead adder. We reduce the carry propagation delay using look ahead carry, more complex mechanism, but still it is faster. two significant signals we define: carry propagate pi is equal to ai exclusive or bi, and carry generate gi is equal to ai bi. Sum and carry are redefined as sum is equal to pi exclusive or ci, and carry, next carry ci plus 1 is equal to gi plus pi ci. The carry signal of the adder become C0 is equal to carry input, C1 is equal to G0 plus P0 C0, C2 is equal to G1 plus P1 C1. If we put the value of C1, then C2 is equal to G1 plus P1 into G0 plus P0 C0, and we just rearrange it. Then we have an expression for C2 in terms of G's and P's, GI's and PI's. Similarly, C3 is equal to G2 plus P2 C2, and if we put the value of C2 and after a little bit manipulation, we have the expression for C3 in terms of GI's and PI's. So C3 does not have to wait for C2 and C1 to propagate. In fact, C3 is propagated at the same time as C1 and C2. So if we have C0, G0, P0, C1, G1, P1, G2, P2, and so on, we can generate C1, C2, and C3 in a two-level implementation. It means the generation time of C1, C2, C3 up to Cn will be same for all. So we have a rearranged circuit. We are taking a 4-bit number A and a 4-bit number B, and we are having A0, B0, A1, B1, A2, B2, and we have generated C0, G0, P0, G1, P1, G2, P2, and G3, P3. And these GIs and PIs will be applied to this particular circuit, and we will have the carries at the same time. And this carry exclusive OR with the PIs will give us the required sum, and obviously we can have the next carry as well. So using this configuration, we can generate the sum in parallel without any propagation of the carry bits, the delay that occurred due to the propagation of the carry bits. Up till now, we have designed a parallel binary adder circuit, a circuit that is used to add two parallel binary numbers. We improve the performance of the parallel binary adder by designing yet another circuit called look ahead carry generator that was used to reduce the delay time of the parallel binary adder circuit. Now we will try to use the parallel binary adder, and we will modify its circuitry in such a manner to use wherever required the same circuit for subtraction as well. From our knowledge about number systems, we know that the subtraction of a number b from a number a is actually addition of 2's complement of the second number into the first number. It means if we can simply take the 2's complement of a number and we add it to the first number, then the two numbers, the second number is actually subtracted from the first number. So how we will use it? Let's see the circuit that we are that we have reproduced over here. In this particular circuit, we are using the same parallel binary adder circuit that we designed during the previous slides. We have added some extra part to this particular circuit, and this extra part is over here. In this part, we can see that we are using some exclusive OR gates, and these exclusive OR gates are taking these two input exclusive OR gates are taking their one input from a control signal M, and the other input of each and every exclusive OR gate is coming from the second number B, which either is required to be added or to be subtracted from the first number. Now this control signal M, we can have its two possible values, either M is equal to 0 or M is equal to 1. Now when M will be equal to 0, we can very easily see over here that when M will be equal to 0, if the bit B0 is 0, then the result over here will be equal to 0, and if this bit is equal to 1, then the result will be equal to 1 over here. It means when M is equal to 0, the number B is reproduced at the output side of the exclusive OR gates, and since number A is also coming directly to the full adders, so when M is equal to 0, simply the number A and the number B are being added by the remaining circuitry of the parallel binary adder circuit. Now when M is equal to 1, now we can see that this M1 will be coming over here, over here, over here, over here at the input of the exclusive OR gates. If B0 is equal to 0, then the result over here will be equal to 1, and if B0 is equal to 1, then the result over here will be equal to 0. It means when M is equal to 1, all the bits of the second number B are actually inverted. It means if any particular bit of B is 1, the result over here will be 0, and if that bit is 0, then the result will be over here will be equal to 1. So what we have done, we have complemented all the bits of B when M is equal to 1. We also know that 2's complement of a number is actually complementing all the bits of that number and adding 1 to the least significant side. So what the trick we have done over here is that this M, when it was made equal to 1, is also coming at C0. So that will add 1 to the least significant side. So the complementing of all the bits of B and adding 1 to the least significant side is actually taking 2's complement of number B. Thus, when M is equal to 0, the number A and B are being added by this circuit. When M is equal to 1, number B is actually being, the 2's complement of B is actually being added to A, and that means that this circuit is actually performing the subtraction. So up till now, so far so good, this circuit is either adding or subtracting the number B from number A depending upon the control signal M, whether it is equal to 0 or it is equal to 1. If it is 0, the number B is being added to the number A, and if it is equal to 1, the number B is being subtracted from the number A. The next thing that we have to take into consideration is the carry over here. The most significant carry is being shown as carry C, and we have also taken the carry output of the most significant bit and the carry out bit of the C3 as well to an exclusive OR gate, and that control next information is being named as V. This V is actually called the overflow. So if a number is in 2's complement form, then whether the result of subtraction or even addition of two signed numbers can be stored within the 4-bit information, or the result is going out of range, this will be indicated by the overflow bit. If the overflow bit is 1, that will indicate that the result is out of range in case of signed numbers. So carry into the most significant bit and carry out of the most significant bit. If both these two bits are same, if both of them are 0 0 or if both of them are 1 1, then the result of this exclusive OR gate, the output of this exclusive OR gate will be equal to 0, indicating no overflow. And if either carry in or carry out, if they are different, if carry in is carry into the most significant and carry out of the most significant bit, if they are not same, if this one is 0 and this is 1, or if this one is 1 and this one is 0, then the result of the overflow bit will be equal to 1, indicating an overflow. We will explain in the next slide that how this phenomena actually works. So we will take some case study examples and we will show that if the carry into the most significant bit and the carry out of the most significant bit, if these two carry bits are different, then that indicates an overflow, indicating that the signed sum of the addition or subtraction of two numbers is out of range. If the two numbers are treated as unsigned number, then whether the result is within the range or out of range, that will be indicated by the simple carry bit. So the simple carry bits indicates whether the result of addition of two unsigned numbers is within the range or not, and this overflow bit indicates whether the result of addition or subtraction of two signed numbers is within the range or not. So let us elaborate the concept of overflow with the help of an example. As I have mentioned earlier, that if we have two n-bit numbers, then these two numbers can either be treated as unsigned numbers or they can be treated as signed numbers. In case of an n-bit signed number, the range is from 0 to 2 raised to the power n minus 1. In case of an n-bit signed number, the range is actually from minus 2 raised to the power n minus 1 to 2 raised to the power n minus 1 minus 1. So these are the ranges of two n-bit numbers when they are treated as unsigned numbers, the range is this one, and when they are treated as signed numbers, the range is in this one. After performing the addition or subtraction of two numbers, the question is whether the result is within the range of two n-bit numbers or there is an extra bit generated. If the two numbers are unsigned, that extra bit is indicated by the carry bit. And as we have mentioned in the previous slide, if the two numbers are signed numbers, the result will be indicated by an overflow bit. Overflow. So two n-digit numbers are added and the sum becomes n plus 1 digits. Overflow is a problem in computers because the number of bits that hold the number is finite and an n plus 1th bit result cannot be stored in an n-bit world. Many computers detect the occurrence of an overflow. A corresponding flip-flop 1-bit memory is set that can be checked by a user or a program. An overflow condition can be detected by observing the carry into the signed bit position and the carry out of the signed bit position. An overflow will occur if the values of the carry into the signed bit position and the carry out of the signed bit positions are not same, as we have mentioned in the previous slide. Let's take some examples. We have taken first example in which we have taken an 8-bit number and the number is its decimal equivalent is plus 127. We know that in case of an 8-bit number, the signed range is from minus 128 to plus 127. We have taken yet another number which is plus 1 decimal equivalent, and the result of the addition of these two numbers is plus 128. Now we know that since the sum of since the range of an 8-bit number is from -128 to +127, it means +128 cannot be accommodated in an 8-bit word. So we can see over here, when we add these two numbers, the result that comes out to be is actually -128, which is not correct. And we will elaborate that since the carry in to the most significant bit is 1 and carry out of the most significant bit is 0, since these two bits are not same, so if rather than checking the result, if we can see that the carry in and carry out, if carry in is 1 and carry out of the most significant bit is 0, since these two are not same, so the result is not valid. Let's take another example. In this example, we have taken the first number, which is -128 decimal equivalent, and we have taken the second number, which is -1 decimal equivalent. Obviously, the sum of these two numbers will be -129, which is out of range of an 8-bit word. When we add these two numbers, we simply can see that the sum comes out to be +127, which is not a valid result. On the other hand, rather than checking the result, if we see that the carry into the most significant, carry out of the most significant bit, carry into the most significant bit is 0 and carry out of the most significant bit is 1, since these two carries are not same, so rather than checking the result, we will just check whether these two carries are not same. If they are not same, the signed result will not be correct. Let's take yet another example. In this case, we have taken first number with +127 and the second number, the decimal equivalent is -1. Obviously, the sum of these two numbers is +126, and when we add these two numbers, the result is +126. Now, interestingly, there is a carry. Now, this carry actually indicates that if we take these two numbers as unsigned number, then there will be a carry and the result will be out of range. For example, over here the signed number is +127, and this number when it is taken as unsigned number, it is 255. 255 when added to +127, the result obviously will be more than 255. Now, if we take these two numbers as unsigned numbers, the result will definitely be out of range. But if we take these two numbers as signed numbers, the first number is +127, the second number is -1. Although there is a carry which is indicating an unsigned out of range result, but since the carry into the most significant and the carry out of the most significant bit, since these two are same, the sum result is +126, which is a valid signed range result. During the last example, we have taken one number +64, yet another number +63, and the sum is +127. There is no carry into the most significant and there is no carry out of the most significant, and the result is valid. So the concluding point is, if we have two n-bit words, and if we add these two n-bit words and we take them as signed numbers, if the carry into the most significant bit of the words and out of the most significant bit of the words, if these two carries are same, the signed result will be within the range. If these two carries are different, the signed result will not be correct and will be indicated by an overflow. Decimal adder. Up till now we have added two numbers and we have taken two n-bit words as binary numbers. Now we know that in case of addition, normally in our daily life we use decimal numbers. So when we add two BCD numbers, 9 inputs for BCD codes and one carry in, 9 outputs, 1 BCD and 1 carry out. So design approach is, either we form a truth table and we can have 2 raised to the power 9 entries, and then we can tabulate and we can design a decimal adder. The other approach is use binary full adders, and the decimal sum must not be larger than 19, because if one number is maximum value 9 and the other number is also with maximum value 9, and if there is a previous carry, still the sum cannot be more than 19. The BCD sum cannot be more than 9. In general, the BCD sum should also be within 9. So we have a parallel binary adder in which we are providing a 4-bit number A and a 4-bit number B, and we are producing a sum over here. If we simply use this is a 4-bit parallel binary adder, but we have to readjust this circuitry in such a manner that it accepts a 4-bit BCD number A and yet another 4-bit BCD number B, and provides us the BCD sum of the number, and that adder will be termed as a decimal adder because it will add decimal digits rather than adding binary digits. So here is the truth table. We have taken the possible sum of two BCD numbers. As I mentioned earlier, that if the first number is having maximum value and the second number is having a maximum value, but 9 first digit and 9 second BCD digit, and if there is a previous carry, then the maximum sum is 19. So we have taken the minimum to maximum possible value starting from 0, 0, 0, 0 and up to 1, 0, 0, 1, 1. So what we have done over here, we have taken the 19 possible sums of two BCD numbers along with a carry. Obviously these 5 digits can have 32-bit combinations, but the remaining 13 combinations will never be arising because the sum will never be more than 19. Binary sum of two decimal digits will never be more than 19. So if the sum is up to 9, the decimal sum and the binary sum will be equivalent. But if the sum becomes, binary sum becomes 10, it should be reflected as BCD 10, and BCD 10 is actually 0, 0, 0, 0 for the first digit, because if we have a decimal number 10, then this 1 should be written as 0, 0, 0, 1, and this 0 should be written as 0, 0, 0, 0. So it means when we have a binary sum 10, its BCD equivalent should be 0, 0, 0, 1, and then this 0, 0, 0, 0 for the next BCD digit. Similarly, if it is 11 or 12 or 13, all these are the binary sum of two BCD numbers. These are the equivalent. This is the 12, 11, this is the 12, this is the 13, this is BCD 14, and so on. This is BCD 19. So this is the binary sum 19 and this is the BCD sum 19. So if we closely look at these tables, when the sum is less than or equal to, binary sum is less than or equal to 9, then there is no difference between the binary sum and the BCD sum. But when the sum is, binary sum is 10 or more than 10 up to 19, we can see that there is a very interesting similarity. If we take it as a binary number and if we also take it as a binary number, this binary number is 10 and this binary number is 16. If this binary number is 11 and this binary number is 17. This binary number is 12 and this binary number is 18. It means the binary sum and the BCD sum, when the sum is 10 or more than 10, when the binary sum is 10 or more than 10, then if we can detect whether the sum is 10 or more than 10 and if we can add 6 to it, then the binary sum becomes actually the BCD sum. Now the only question left is how to detect whether the binary sum has gone more than 10 or 10 or more than 10, means it is more than 9. This is very simple. We can see this, that if the Z8 bit is 1 along with either Z2 bit or Z4 bit are 1, then if there is a carry bit 1, then in all these conditions the binary sum will be 10 or more than 10. See this adjustment over here. Here we have reproduced the table that we were discussing in the previous slide. When the binary sum is equal to or less than 9, the corresponding BCD number is identical, no conversion is needed. When the binary sum is greater than 9, an addition of 6 0 1 0 0 1 1 0 converts it to the corresponding BCD representation and also produces the output carry as required. Modification is needed if the sum is more than 9. How it will be detected? C must be set to 1 if K is 1 or Z8 along with Z4 is 1 or Z8 along with Z2 is equal to 1. So if K is 1 or Z8 along with Z4 is 1 or Z8 along with Z2 is 1, in all these conditions, the binary sum will be 10 or more than 10. So this means if C is equal to K plus Z4, Z8 plus Z8, Z2, then the carry can be adjusted and we can add 6. When C is equal to 1, add 6 to the sum and the result will get converted into BCD. So here is the circuit. We have taken the augment BCD number, the addend BCD number, and we have applied it to a 4-bit parallel binary adder. The result over here will have a carry and 4 output bits, that is Z1, Z2, Z4 and Z8. So what we have done, we have taken Z8, we have taken Z4, the AND combination of the two, we have taken Z2 and we have taken Z8, the AND combination of the two, and the result of the output of these two AND gates and the K bit, they have been input to an OR gate, and there is an output of this OR gate. This output is called the carry bit. So if this carry bit is 1, that indicates the sum of these two BCD numbers has gone beyond 9. So in order to adjust that, what we need to do, we have to add 6 to make it a BCD. So what we have taken, if this output is equal to 1, we have taken yet another parallel binary adder. It is taking Z1, Z2, Z4, Z8 as its input as augment, and it has taken yet another addend as to be equal to taken from this carry output, and we have taken the inner 2 bits equal to the carry output and the remaining 2 bits are equal to 0. When this carry output will be 0, these two will also be equal to 0 and nothing will be added and the number will be coming over here and there will be a valid BCD sum. When this is equal to 1, that actually indicates that a 6 needs to be added, and when this 1 is coming over here and it is adding setting these two bits equal to 1, that means binary 6, and this binary 6 will be added to the already available sum and the number will get adjusted. So a minor adjustment to the parallel binary adders can be used to utilize a parallel binary adder as a BCD adder.